Yep.
And
All
our next speaker comes from the University of Michigan. That's always a highlight. Kyle, are you there?
Yeah, can you guys hear and see me?
We can do both.
Excellent.
If you want to claim the screen,
Can you guys see that?
introduce your talk as being Hammer, a student-driven radiation transport solver framework. Now, if this is Hammer, it's too bad the talk isn't given by Thor. But anyway, well, you're gonna have to step up to the plate here.
There's actually a funny story about that, but we might get to that later. Well, thanks for the introduction, Professor, and thanks everybody for tuning in. And I'm going to be talking today about Hammer, which is a research framework for radiation transport solvers that we're developing at the University of Michigan in Professor Kudrowski's group. So at the bottom here is just all the current contributors to the code. I couldn't, fit everyone who's ever touched the code in this space, but we have a healthy mix of PhD and master students and a lot of undergrads. And I think it's cool that we get a lot of students, involved in contributing to this project. So first, why do we care, within MTV about radiation transport solvers? So what these are computational tools that allow us to simulate how essentially radiation interacts with matter and moves around in matter. And they're used for a lot of applications, but the most relevant is probably in the design and analysis of radiation detectors. And I know a lot of people in MTV are, they're designing and building sort of the next generation of monitoring and verification technologies. These are often really complex detectors, often like arrays of detectors used for multiplicity counting or imaging, and often they're measuring really complex sources that are maybe time dependent or have some multiplication that you have to be able to capture that complexity within your computational tool. So radiation transport tools are really, there's two classes of solvers. There's deterministic solvers, which are fast, but you have to discretize the phase space of your particles, space, direction, energy. And Monte Carlo solvers are stochastic solvers, which don't require that discretization. And they're more accurate because of it, but often slower. So our goal with Hammer is we want to develop an open source collaborative framework so that researchers, both on the computational side and more on the user, detection side, to be able to rapidly prototype and test out different ideas, different radiation transport techniques easily within the code, and also encompass, many different solvers, both deterministic and transport, and keep that all sort of in one framework. And one thing I want to point out is Hammer is developed, maintained, and managed almost entirely by students, which is really cool. Currently, the project manager is a PhD student, Aaron Tumalak, and we're moving to a program where each semester a different PhD student will act as sort of the project manager. So that's a really cool experience that we get to have. And before I go any further, I just want to say my goal in this talk is really not to get too much into the technical weeds, but rather to just take a broad look about what Hammer is and what we want to do with it, and then sort of just go into just a couple different samples of some of the specific projects. So first, why are we doing this? Well, Hammer kind of fits in the space between you have on one side production codes that are really fast, optimized for high performance architectures, very well validated, ideal for production analysis. If you have a big complex problem that you want to solve in a standard way, you use one of these tools. However, sometimes when you're trying to put in a non-standard way or a new way, it's often a steep learning curve to know how to contribute to these codes, especially when you're modifying source. And often because these products have been around for a long time, which means they're tried and true and tested well, but that often means you sort of have to manage around legacy coding practices, which can contribute to that learning curve. And then on the other side, you have sort of like the one-off research test codes that are more of just like a proof of concept for a new algorithm or a new technique. They're very simple, like a 1D problem kind of thing. They're not fully featured and they're sort of disposable. You test out one thing and then you throw them away. So the idea of Hammer essentially is that we want to have the flexibility to test out new ideas very quickly while also capturing the complexity that you need to capture if you want to actually model like verification scenarios. So to do that, we're building it with modern software engineering best practices, and we want to make it open source and collaborative as possible. So how are we doing this? What technologies is Hammer built on? We're using object-oriented C++17, which gives us a lot of nice abstractions and language features that make the code cleaner and more maintainable. It's cross-platform. We can build on most common operating systems. C++ actually gives us an in-language feature to deal with basically multi-threading without having to bring in new technologies for that, which is nice. We use Git for version control, and we're hosted on GitHub, which allows us to roll in a lot of these really nice technologies that deal with like continuous integration and unit testing and things like that. So on the right, you see this dashboard. This is kind of what it would look like if a developer or a contributor wanted to pull in a new feature into the code, and you would get all these little things that say, yes, the code builds and all the unit tests are passing, and yes, they added new unit tests to cover the new feature they added. So that really automates a lot of the DevOps stuff that makes the code, again, cleaner, more maintainable, easier to read, easier to use. And then one thing I want to go into a little more is we have all our interfaces human-readable XML. So here's an example of an input file, just a very basic problem. You have two concentric spheres, you have some variance reduction happening. This is a Monte Carlo problem. You have some estimators of flux over some mesh. You're telling it to print it in VTK format so you can visualize your estimators with pair view. The idea is that we want the interface to this code to be like, you don't have to go back and forth constantly with the user's manual to be able to write a simple input deck. You can it sort of just makes sense. So having said, what Hammer is, what can we actually do? Right now, we just do fixed source calculations. We can do Monte Carlo in 3D, multi-group or continuous energy. Then we can do SN in 2D, both forward and adjoint. So that's what you see down here is a 2D SN problem with just like a point source as an example. And you can see, the forward flux, a little bit of ray effects, just ignore that. And then the adjoint flux. And right now we just do neutrons and photons, but we're sort of expanding rapidly. And one of the nice things about bundling different solvers together in one framework is we can reuse and share a lot of code between those solvers. So we have a lot of low-level sort of math and utility stuff, but one of the big things is we have meshes that can be used on both deterministic and Monte Carlo sides. We can deal with structured, some common structured meshes as well as unstructured tetrahedral meshes. And getting into more on the Monte Carlo side, we have fully featured variance reduction, pretty much everything you would want that's standard right now: importance splitting and rouletting, forced collisions, forced flight, or DXTran if you're an MCMP user. And these are things that you often hear Monte Carlo is a method of last resort or slow, but these are the things that make it faster and help you solve these complex problems in a computationally tractable amount of time. And then we also have a pretty fully featured suite of estimators for things like flux in a volume, both track length or collision, flux or current on a surface, flux at a point, and any of these things you can bin over your particle phase space, energy, collision order, whatever you want, and you can modify to get things like a reaction rate out of it. So this is what we're working on right now. This is what we spend our time doing is adding these new features. So one project right now is fleshing out our constructive solid geometry and adding things like lattices and regions. I know a lot of people, are dealing with like simulating arrays of detectors. So it's nice to be able to just, model that once and then rotate it around or, translate it over or whatever. We're adding in transport and stochastic media, which is really interesting. That's when you can't really treat a material as homogeneous when you have like maybe bubbles in your coolant or concrete with voids in it. You sort of have to treat that there's these weird little Swiss cheesy bubbles in it at a fundamental level. We have an in-house physics event generator that's under development that can handle fission and radioactive decay, which is nice. So instead of relying on evaluated nuclear data necessarily, you can directly couple like a first principles physics model with your Monte Carlo solver. And then we're doing a lot of exploratory projects and other projects in sort of the space of hybrid methods between stochastic and deterministic, which I'll touch on more later. And then beyond that, there's a whole list of things that I could mention that are on our list to add. Obviously, we want eigenvalue problems. That's really important to have. I'm excited about putting in sensitivity analysis capabilities. So you can sort of understand how a perturbation in something like nuclear data or the physical parameters of your system actually affects your observable, like, what's the flux in my detector, things like that. Neutrino transport is pretty relevant to a lot of the stuff that's happening in MTV. Obviously, we eventually want to scale up so we can run on big clusters with MPI. Yeah. So we'll mention all that. So getting into some of the more specific things we're doing. So this is one of the hybrid methods between Monte Carlo and deterministic that kind of we originally started with the code. And this was a collaboration with, to your point, Professor Thor, which is a code at NC State. And Thor is a deterministic SN or discrete ordinance solver that works on an unstructured tetrahedral mesh. And the issue with these SN solvers is that they suffer from these things called array effects. And if you imagine these two pictures on the bottom here, you imagine sort of a plane that's removed from a point source, you would expect your flux to look like something like this. That's sort of 1 over r squared. But with the discrete ordinance methods, you sort of get these artificial nodes and troughs that are not physical. They're just a result of the fact that in discrete ordinance, you're saying particles can only travel along these specific angles that I'm giving to the code. So essentially what we showed is that if we can run, in Hammer in our Monte Carlo solver up to n collision orders, and then add that in as a source term into the Thor code, and we can couple, or we can mitigate those ray effects, as you can see here. And this was, pretty, an example of sort of the complex problems we're trying to capture. So the test problem we had was like a burnt ball surrounded by various types of shielding with like a helium-3 neutron detector. So this is not a novel necessarily technique for weighted CADIS, but this is, I think, really exciting and really cool. And it's having this, this is something we're actively working on, and having it in will allow us to build off with other sort of interesting hybrid techniques. So the idea behind this is, let's say we have some system here where we have like an absorbing medium, and then we have this streaming medium that has like a weird maze or channel to get from a source down here to a detector up here. Standard transport techniques, not many particles are going to make it over here. You're really not going to get much of an answer in your detector. So what you can do is you can run the adjoint problem, and the adjoint flux is closely related to a concept of importance. And you can think of that like, how important is a region of space to my detector up here? So close to the detector, important; far away, not so much. And you can use this to accelerate your Monte Carlo code by saying, if I have a particle that goes from low to high importance, I split it, and make it more likely that one of them eventually reaches my detector, or vice versa. If it goes from high to low, you flip a coin and maybe kill it and say, that particle's way out here, it's a lost cause. So it allows you to run, Monte Carlo problems quite a bit faster. So that's an exciting capability we're putting in right now. And then here's also a really interesting one, I think. So we're interested in putting in some machine learning capabilities, the idea being to be able to train a neural net to optimize the Monte Carlo variance reduction. So basically, we're in a very exploratory phase on this one right now, but the idea is we're generating a suite of test problems, think something like this, but many, many, many different problems that are sort of maybe more difficult to solve in an analog Monte Carlo solver. And we're generating, a suite of solutions for those problems, both analog and with various variance reduction techniques. And the idea is that we can feed that information into a neural net and train it to say, oh, this type of problem is best suited for this type of variance reduction, and sort of optimize, how you run a Monte Carlo problem to make them faster and, give you better answers. And we're also interested in sort of finding ways to couple a deterministic solver into this to sort of add more information to that net. So that's a very exploratory, we're kind of just starting with that, but I'm really excited to see where that goes. So that's really all the technical stuff I wanted to talk about here. As far as like National Lab and MTV Impact, we're pretty active with the labs. Just this summer, we have 4 students, 2 at Los Alamos, 2 at Livermore, doing a lot of things that are, very related to what we're doing in Hammer. And then we also have some longer term ongoing collaborations with Oak Ridge and Sandia, which is really nice. So yeah, that's really all I wanted to say. So Hammers, we're essentially here to support the development of the next generation of monitoring technologies by providing the tools to actually be able to model them. So yeah, thank you for your time. thank you for everyone for tuning in, and we're looking forward to hopefully getting more collaborations with all the people behind these nice logos here.
All right, thank you, Kyle. Are there any, we'll open the floor for questions, either through the chat, or if any of the audience would like to unmute and ask a question, we would welcome that. While you're thinking of questions, Kyle, I've got a couple for you. How
Sure.
big is the code?
How big is the code?
How big is
I think last I checked, in terms of like lines of code of actual C++, is I want to say something like 40,000. That might be wrong. I'm not sure. Yeah, that might include some third-party libraries we have in there. So, but it's not terribly big. The way I think it's also very sort of modular and broken up into pieces that are a lot more digestible, I think, for new developers coming in.
Okay, so 40,000 lines of C++, and you thought
Don't
that
quote
was
me on that number though. That's
okay. That's fine. In any of the Monte Carlo, in any radiation transport or deterministic solutions, you need cross sections. Where do you get the?
right.
How do you import and process the cross sections?
So right now we essentially just let the user provide cross sections, and like we're not really dealing with providing cross sections bundled with the code, because I think there's some export control issues that come along with providing both of those things together. But essentially the user can provide, right now it's essentially just like .dat files, essentially big lines of text that you can provide either in continuous energy or multi-group format. But we're looking towards switching over to like a more generic XML data format, and eventually to something like HDF5 or XDMF that can handle a lot of data and compress it.
Okay.
And do like parallel IO and stuff like that.
Okay, and then one other comment I would have is you say you're using modern software engineering as compared to the legacy coding from before. Do you realize that within a few years, your modern software engineering is going to be legacy coding?
Oh, absolutely. But I mean, we can only use the tools that we have right now. And fortunately, there's are a lot of tools that are available right now that, that are sort of the cutting edge in making code a lot easier to contribute to and a lot easier to read.
Yeah, I think you're exactly right. In some sense, it's more specialized than it was in the days of the legacy coding.
Yeah.
And more difficult to get into this, into the game. Whereas, so I applaud your idea of GitHub coding for NNSA. That certainly is an interesting concept. Questions from the floor? The other thing I would, I'll hold this question maybe because I've been noticing how much machine learning has been occupying this, the talks that we've been having. So I'm going to accumulate a question on that for the end, and maybe all of the speakers could comment on it when I get there. All right, Kyle, before I close, any the audience would like to chip in? If not, Kyle, thank you. A virtual set of applause from your audience. And if you wouldn't mind releasing the screen.